Scalable vector graphics, or SVG for short, is the standard for making vector-based graphics on the web. In case you don't know what vector-based graphics are, they differ from bitmaps, the format for non-vector type images, and how they are much more scalable than bitmaps. This is because bitmaps are made up of innumerable pixels that when coalesced together form an image. Now on their own, these pixels are just individual squares that can hold a solid colour. This is why they are presented in a mosaic pattern with other pixels, and it is only after these pixels have been grouped together where a clear image can be formed. As you can imagine, the more pixels there are in an image, the clearer it is going to look because the image has more pixels to work with to illustrate the more imperceptible details. Now this is fine, but what happens if we want to scale a bitmap image? Well, we can, but the pixels will get larger if we do. Twice as large if we were to scale the image by a factor of 2. Now there are algorithms that try to mask this messy upscaling process of pixels by blowing the oversized pixels into each other to get the same number of pixels as the original image, just with colours that represent the symbiosis of the upscaled image. And this can work fine in some cases, but essentially the result is clear. We really shouldn't be upscaling bitmap images because it would detract from bitmap strength of being able to create lifelike scenery. Instead, things will just get blurry. So that is how bitmaps work, but how about vectors? Well, unlike bitmaps, vectors are not made up of individual pixels. Now that may be how they are viewed on a digital screen, but that is not the format that they are stored in. Instead, they are formed from mathematical lines and curves. These mathematical rather than mosaic properties of vector-based images means that they can be scaled up infinitely. 2 times, 4 times, 8 times, it really doesn't matter. Vector images will never lose their crispness when upscaled, because the mathematical equation responsible for drawing the vector will just multiply its values by the upscale factor to create a new image. So there is no transmogrifying of pixels to upscale the image, which is what leads to a decrease in quality for bitmap images. From this, you may think that vectors are undoubtedly superior to bitmap images, but it is important to remember that neither is better than the other. They are both good, providing that they are used appropriately. Bitmaps are good for drawing real-life graphics. They can represent the material plane felt through the sense of vision. Bitmaps are not so good for illusions though. Things like logos and graphic design, etc. If you wanted to draw a straight line, then you would want the straight line to actually be straight, not coarsened by the edges of pixels that are necessary to draw a line in a bitmap image. In a case like this, it would be best to use a vector image. Vectors allow illustrations to really be themselves and not be hindered by the restrictive nature of pixels. Lines, curves, solid fills, you name it, vectors draw all of these out freely, whereas bitmaps just try to stifle them all into its regimented framework. Vector's shortcoming is the same as bitmap's strength, that is creating realistic imagery. When it comes to this, bitmaps are clearly the most suited because you can't really create something as detailed as a waterfall with mathematical lines and curves unless it was a cartoon waterfall. So you now know the difference between vectors and bitmaps, but what about SVG specifically? What are the characteristics of this vector-based image format? SVG's defining characteristic is its XML tag structure. This format will be very familiar to you if you have any experience in HTML or XML itself, which is likely if you're watching this video. In XML, the tags will be the shapes themselves, so one tag could be a rectangle or something. Then the attributes will be how you want the shape to be presented. So one attribute can determine the positioning and the other the colour, etc. Although this XML format is the core structure of an SVG file, writing in tags and attributes to an SVG file is often not how they are worked with. Instead, they are normally generated from vector-based editing software like Adobe Illustrator. These software give the user an option to export their work in the SVG format, and if they do, then the software will automatically generate these tags and attributes based on the illustration that the user has drawn using the software GUI. Doing this is fine, but it can lead to complications in incorporating the SVG content into the HTML file. Because as I said before, SVG is the web standard for creating vector graphics on the web. This means that SVG is actually supported natively in HTML files. All we need to do is write an SVG tag in our markup file, and from then on, all content that would normally go into an SVG file can go into this SVG tag. This means that graphics created can be embedded into your web page instead of being isolated off in their own file. Actually, using SVG in your website can really give your website a bite to it that can make it stand out from the crowd. It can be like a hidden weapon because not many developers actually know the ins and outs of SVG and how it really works, though they may know what it is. It can give you the power to draw out graphics natively in the browser, so not from an external image source, but actually hard-coded into the markup file, and much more elaborate than you would be able to create with primitive CSS tools like clip path and border radius, etc. But you can also animate these elements, just like how you would animate an element normally, using either CSS or JavaScript if you wanted to get more advanced, but more on that later. Now, if you're familiar with Canvas, then this added layer of creativity to your web page may not excite you all that much, because you could already do a lot of these things just for using Canvas. And this isn't wrong. Canvas and SVG can pretty much do the same things as each other. The difference lies within what is most appropriate for the situation at hand. Canvas is more suited to things like game development because graphics do not have representation on the markup file. Everything is hard-coded directly into the single canvas element. In SVG though, shapes have to be represented on the markup file. In fact, creating tags for them on the markup file is how shapes are created in SVG. This key difference means that Canvas is faster to animate than SVG, but shapes on the canvas are harder for users to interact with, as they are heavily separated from the markup file. As such, SVG is less pertinent to game development, but more appropriate for congruous graphics and animations on a normal day-to-day website. So in this crash course, you will learn SVG from the ground up. No messing with expensive illustration software. Instead, we will learn the full anatomy of an SVG file, so that by the end of this crash course, you will be able to create an SVG illustration by just writing in plain code into an SVG file without the use of any proprietary software. So here we are in an empty project folder in VS Code, a free text editor by Microsoft. And we'll create the markup file. And then we can generate the boilerplate code in VS Code by just pressing enter after typing an exclamation mark. After creating the header, we'll actually create the SVG tag now. And so that we can actually see it, we'll need to give it some dimensions. So we'll give it a width and a height attribute. Now we set it to be 600 pixels by 600 pixels, so a square. Now this will be hard coded in, and you could do dynamic, so we could do like a percentage value or base it off of the viewport. And this is fine, but because positioning shapes in SVG is based off of the offsets in relation to this SVG stage element here, it can be a bit hard to position the elements if you do size the stage dynamically, because everything will have to be positioned by a fraction of the wider viewport, which is dynamically sized. It's just a lot easier if we do everything hard-coded. And obviously we could do things like media query later on to change the styling if our viewport is too small or too large, etc. But we'll do the styling now, so we'll create the link tag. And so this is the styling, and we'll open this up with Live Server, a VS Code extension, in case you're wondering. And as you can see, it's looking good. I'll do this to the side, and then I'll press Ctrl-B to remove that file explorer, so you can see what's actually going on. And now that we've got this SVG stage element here, we can start by creating our first shape. And we'll begin with the most basic shape of them all, just a simple rectangle, and it's represented by this rect element here. And it's important to note that all these SVG elements have to be contained with this parent SVG tag here. If they were outside, then they wouldn't have any meaning to them. Now we can't see a rectangle on the stage at the moment, and that's because we need to give it 4 key attributes. And now we could actually see a square. So what this means is it means 10 pixels from the left edge of the stage, and this one means 10 pixels down from the top edge of the stage, and then it's a square because it's both 100 pixels in width and also height. If you wanted to center the square though in the middle of the stage, then we will change its X and Y offsets to these values. You see before, the origin of the rectangle, which is its top left corner, was set to be 10 pixels on the left edge of the SVG stage, and 10 pixels down from the top of the SVG stage. Now though, our offsets are set in a way that will make the center of the square aligned with the center of the stage, and as you can see, it's at the center here. This is because we know that an offset of 300 and 300 on both axes will be dead center of the stage, because our stage is 600 by 600. We can't use these offsets though, because if we did, then the top left corner of the square will be on that center point, not the center of the square itself. To prevent this, we subtract 300 by half the respective width and height of the square to pull the offset back enough to make the center of the square meet the center of the stage, hence the square has been centered. If you wanted to customize the square out a bit though, then we could add these basic properties. So this changes it to red. The stroke width increases the thickness of the border, and the stroke is the color of the border. And as you can see, we can give hex values as well as just typing out the basic names of the colors. Now circles are a bit different from squares, and that's because the origin of circles is positioned in the dead center of the circle and not at the top left of the circle, which is what it is for polygon shapes like rectangles. That's why we could just use 300 as the offset to center the circle in the middle of the stage. And those offsets are represented by these CX and CY attributes respectively. As for the circle's dimensions, that is determined by its radius, which is configured by this Y attribute here. We have set the circle to have a radius of 50 pixels, emanating from the circle's origin, which is its center point as just said. So 50 pixels all around from the offset, hence a perfect circle has been created. Now circles are pretty rigid in the sense that it cannot be squashed or stretched. They have to be of equal proportion all the way around. An ellipse could solve this problem. It allows us to create a spherical object that isn't a perfect circle. So its offset is positioned in exactly the same position as the circle in the center, and its origin point is also the center. But its Rx, so its radius on the x-axis or semi-major axis, is a lot wider than it is on the y-axis or the semi-minor axis. Oh, and by the way, shapes in SVG don't have to have a closing tag, which is the reason why we can write them out to self-closing tags, which is what we do here. This line element will do just that, it will just draw a straight line, and its attributes are grouped together in pairs. The first two attributes define the starting coordinate, and the last two attributes define the ending coordinate. Now, you can't actually see the line at the moment, and that's because we need to define a colour and the width of the stroke, which is the only thing that comprises a line because it has no fill. So now we can see the line, it's looking pretty good. But if we wanted to do a line drawing, then making many different interconnected lines would soon become tedious. This is where the polyline shape element comes in. It is one shape that is comprised of many different lines. Note that the individual numbers in the points attribute, the attribute that defines a shape, can be separated by either spaces or commas. It doesn't matter which, we could even use both interchangeably, but for now we will use spaces just for the sake of simplicity. And of course the numbers are grouped together in twos to make a coordinate. The x value comes first and then the y value comes next, and then after that a new coordinate starts. And so here we simply just draw a line where it starts at 1010 and then travels to 590, 590. Here though we've created something a bit more elaborate, and we'll remove the fill so that you could actually see the zigzag pattern. We'll increase the width of it as well, and add these two properties to change the characteristics of the line. Now the stroke line cap attribute changes the endpoints of the joined together line, and the stroke line joint attribute changes where the two lines connect to each other. Both of them are now set to round, which produces this kind of bubbly effect as opposed to the harshness of the straight edges, which is used by default. Now polygon is exactly the same as the polyline element, other than the fact that the polygon shape automatically draws a line between the first coordinate and the last coordinate for us, if we haven't done so ourselves already. So that's why we have this line here, even though we haven't actually changed any of these points. Now you may notice that all of the aforementioned shapes are kind of limited in the sense that they don't give us full flexibility over the shape that we want to create. Even the polyline and polygon shapes, which are far more customizable, even they don't give us any way to incorporate things like curves into our shapes. This is a perfect lead on to the most powerful shape in SVG by a long stretch. That is the path. The path allows us to create any shape our mind desires. Shapes, ellipses, triangles, you name it, the path can create it. For paths, it is the D attribute that allows us to construct a shape of our choosing. As you can see, it takes in letters as well as numbers. These letters are called commands. They specify how the path deals with the coordinates given to it. Take this M command for example. It stands for move to. It is listed as the first command because we want our path to start at 10 pixels offset from the stage's origin on both axes. Now the move command is most likely to be used at the start of the D attribute to specify where we want to start drawing the path. This is unless you want a split line or shape, where there is a gap in the middle, in which case we would do something like this. Notice that we've used a lowercase m here. When we used an uppercase M at the start, these commands do not actually mean the same thing. Uppercase commands are position absolute, which means that they are position in relation to the stage's origin. Lowercase commands are position relative, which means that they are position relative to where the path is at the exact moment where we do the command. This is why the lowercase command can have a coordinate of 10, 0 and yet still split the line in the middle and not at the very start of the path where it began. We are saying move 10 pixels to the right of where it currently is and 0 pixels downwards. As for these L commands, that simply stands for line 2, and as promised, all it does is draw a straight line. Since we have used the lowercase relative variant, we have used minus numbers for the y coordinates when we want to move the location of the new line upwards. If we were to use the uppercase absolute variant, then we would not have to do this though. So here is that very same zigzag line written using the absolute version of the line 2 command instead. If you wanted this path to automatically draw a line between the opening and closing coordinates, like what the polygon shape does, then you would add this Z command to the end of our D attribute. Now there isn't actually any difference between the uppercase and lowercase versions of this command, they both do the same thing. As I said before, paths can handle curves. There are 3 different kinds of curves that paths can handle. 2 of them form a Bezier curve, which is a mathematical way of drawing a curved line, and the third one is an arc, which is a subsection of a circle. Now the first curve that we will cover is a cubic Bezier curve. It is the more complicated out of the 2 Bezier curve commands, because it uses 2 control points instead of the other one which only uses 1 control point. This image should give you a rough idea of how these curves work. The 2 control points are on either ends of the curve drawn. As you can see, the command for this type of curve is written as the letter C. As you can see, the command for this type of curve is written as the letter C. The first pair of values define the first control point in relation to where the path currently is. The second pair is the second control point, the control point that controls the ending point of the path, which is the third and final pair of values that are related to the C command. For the sake of demonstration, we have used the relative variant in this command because it is a lot more complicated than the absolute version, which is fairly self-explanatory. Essentially, both the first control point and the ending coordinate are derived from where the path ended up at in the commands that came before this one. It is only the second control point that derives its position from somewhere else, and that is the location of the first control point. If you wanted to string together multiple cubic Bezier curves to create something of an S shape, then you would use the S command. This command must come after a C command though. That is because it automatically sets its first control point to be a reflection of the second control point of the C command that came before it. This is why the S command only requires 2 coordinates, the second control point and the finishing point. The blue line here shows us how the automatically generated reflection control point is created when we use the S command. We're also going to switch back to absolute positioning now because that makes things a lot easier. The other type of Bezier curve is the quadratic curve. It is simpler than the cubic curve because we only have to worry about 1 control point instead of 2. Therefore, it only takes in 2 coordinates, the singular control point and the coordinate that we want our path to end up at when the command is over, and the command for this type of curve is Q. Like with cubic curves, we can string together multiple quadratic curves using the T command. And as with before, this command must come directly after a Q command. This T command only takes in 1 coordinate, that's where the path will end up at. Its singular control point is automatically made to be a reflection of the control point of the Q command that preceded it. How the reflection is generated for this command is shown on the image on screen. Arcs are the final way to draw a curve and a path. They can be thought of as isolated parts of circles or arcs. The command for them is the A command. Now arcs can actually be pretty hard to understand because there are 2 invisible ellipses that go into creating a finished arc. We are given 2 ways of connecting these ellipses together, making 4 different ways of drawing an arc in total. We will ignore these middle 3 numbers for now to make things easier to explain, but the first 2 numbers of the A command define the radius of the arc on both the x-axis and the y-axis respectively. As for the last 2 numbers, they are coordinates that define where the arc will end up at when the command is over. As for the third value, this 0 here, it configures the rotation of the arc, and we are now rotating the arc 45 degrees counterclockwise. We'll rotate it back. As for these last 2 values, the 0 and the 1, they configure how the arc is drawn from the 2 ellipses that are involved in the construction of the arc in the first place. They can only hold a value of either 0 or 1, and these 2 states are what determine the 4 possible ways of drawing an arc. The first are the 2 numbers, the 0, that is known as the large arc flag. It determines whether the arc should be greater than or less than 180 degrees. In our case though, changing its value won't really do anything, because for it to have an effect, we would need the arc drawn to have some presence in both ellipses that are involved in the construction of the arc. This is not the case with this arc though, as you can see. It is only within the top arc and not even in the overlap section with the other ellipses. As for the final parameter, it is called the sweep flag. In this case, changing its value will have an effect because it essentially determines whether the arc is travelling in either the positive or negative direction. As you can see, it's now going in a completely different direction, and it represents the other side of the ellipsis. As for styling, there are many different ways to style an SVG shape. What we have done so far is we have just typed out the individual attributes, but this is just one of the many ways of doing it. Alternatively, we could write out all of the styling in the style attribute to achieve exactly the same result. To get even more elaborate, we can isolate all of the styling for our SVG element into their own style tag. Now this style tag has to be within this defs tag, which stands for definers, and this is also within the parent SVG element. And so we now created the styling for an element for the SVG element with an ID of Ellie, and we've removed the inline styling here, so that's the reason why it hasn't got any styling. But then we can give it an ID of Ellie, and then the styling will be applied to it, so it's back to what it was before. One of the best things about this style element is it gives us access to all of the power that comes with normal CSS. So we could use things like this hover pseudo class, and it can give our element some level of interaction with our user. So when we hover over it, it changes color to red, the color specified in the hover pseudo class. Now, if you're familiar with CSS animations, then it should be pretty self-explanatory as to how you would animate these elements around. In this example, we have added a transition to the element, so that when we hover over it, the shape will begin to animate towards the right, and then we can release it any time, and it will go back to just its origin. Alternatively, we could also apply a classic CSS animation as well, so it fades out. As for text, it is simply created with this text element. This one will not be a self-closing tag because we need to write the text content inside of the element. We can also style it using the standard procedure. Just as a quick tip, we could apply the same styling to multiple elements by using this G element. Any styling given to it will automatically be applied to all of its children. Well, it looks like you have to customize the font family yourself, but you get the idea anyhow. Now I'll actually go back to this green rectangle because we're going to cover gradients now, and it would probably demonstrate gradients a lot better than the shape that we had before. Now for gradients, there are two types of them. There are linear gradients which transition from one side to other, and radial which emanate out from a certain point, and all of these gradients have to be defined within the defs tag. So we'll start off by creating a linear gradient, and all gradients should have an ID so that we could apply it to our shapes. Then we use these stop elements to define the characteristics of our gradient. For now, our gradient will have three inherent colors, red, black and blue, except that black won't actually be seen because its opacity is set to 0. They are also set at equal proportions from each other as configured with this offset property. Now we apply this gradient to the fill property using the URL method, and inside it takes in the ID of the gradient that we want to use. And although we've added it with the style property here, we could set gradients using any of the aforementioned ways of styling SVG elements. We can also add these extra attributes to our gradient to change its direction, and the following has made our gradient travel vertically. Finally, we can also use these decimal values as an alternative to the percentages. And obviously this is just the same, only it's divided by 100 instead of the percentages, which are times by 100 from these decimals. Moving on to radial gradients now. And as you can see, by default, the point at which the gradient expands outwards from will be the center of the shape that the gradient has been applied to. We can use these CX and CY attributes though to offset this point by a specified amount and use this R attribute to change the size of it. If we wanted to customize this origin point even further, then we can use these FX and FY attributes, which control the focal point to move the point at which the origin is at its most concentrated away from its default position, which is the center of the origin point. Note that all of these attributes are between 0 and 1. It is because of this gradient unit attribute here. Although we have only just added it, this attribute is assigned this value by default anyway. It automatically scales our gradient to the object that it is applied to. Therefore, when we customize our gradient, it is always relevant to the size of our object. If we wanted to change this and use absolute positioning, then we would use user space on use as our value instead. Obviously, this is going to break our gradient at the moment because the values are not accurate for this setting. If we wanted to apply some effects to a shape, like a Gaussian blur for example, then we would use filters. Again, they had to be within this defs tag and have an ID to them so that they can be applied to our elements. This one will blur our shape by a blur factor of 5. And we apply it with the standard procedure. The last thing that we will cover is how we would hide specific parts of shapes. There are two ways to do this, clipping and masking. The difference between the two is that clipping cannot have semi-opaque pixels. Everything has to be either shown in full or completely hidden. Masking though is the complete opposite of this. It can have semi-opaque parts. We will start off with clipping. It can take in any shapes to define the size and shape of the clip. Again, it needs an ID so that we can use it on our shapes. And we apply it with the clip path property. Now the bottom of our square will disappear. This is because it has been hidden by the clip, which had a black rectangle drawn inside of it. This black rectangle, black because that is the default colour of shapes in SVG, has hidden our square because in clips black means hide but white means show. As for masks, to take advantage of its semi-opaque nature, it is likely that we will create a gradient of some sort to set as the fill of the mask. This is a linear gradient that just fades from black to white. We have currently set it to travel vertically, in reverse, so from white to black. This fill can now be assigned to our rectangle. And the mask will actually contain the exact same rectangle as before, except the fill is that gradient that we just created. And our shape can now use a mask instead of a clip. And as you can see, it fades down because it starts to turn black at that point, because remember we reversed it on the vertical axis. And that's it for this one, guys. I think that I've covered enough for you to really get to grips with how SVG works. Don't get me wrong, SVG is a dense topic, and there are things like patterns which I haven't covered in this crash course. But the point of this video was to explain the essential information. And once you understand how SVG works properly, learning these extra things should be a breeze to you. So I hope that you enjoyed this video. If not, then please leave me with some feedback in the comments below on how I could improve. But if you did, then please consider giving me a like and subscribing. You'd be doing me a huge favour if you did do this. More importantly though, have a great day and peace out.